This is our fourth video on fluid mechanics, and in this video we're going to start with the Bernoullis Principle or Bernoullis Law or Bernoullis Equation. And before I show you the equation, let me explain to you what the principle stands for. In the previous video we talked about the continuity, and continuity of the law says that, or the formula that we derived says that if the area 1 times velocity 1, that will be equal to area 2 velocity 2, and that would be equal to area 3 velocity 3. In this picture, it looks like area 1 and area 3 are the same one, so I can just ignore that part. And here I see that area 1 is larger than the area 2, the cross-sectional area. So if I cut it like this, so the cross-sectional area for area 1 is larger than area 2. To compensate this equality sign, if you have area 1 larger and area 2 is smaller, then that means the velocity 2 must be larger. And that is what you see here for velocity. This must be velocity in area 1, but the velocity in area 2 is increasing. And then the velocity in area 3 is back to the velocity in area 1. But it happens opposite for pressure. So for the pressure, and that is where Bernoullis Principle stands. For pressure, you had some pressure in area 1, but when you have higher velocity, pressure drops. It happens due to the fact that the velocity is higher, so less molecules are hitting the sides of the walls of the container or the pipe. And then when the velocity slows down or drops, then you have the pressure going back up again. Have you ever seen the pictures or videos of a roof blown away of the house during the hurricane or tornado? You might be surprised to hear that the roof is actually not blown off by the strong wind, but instead by the air inside of the house. This can be explained by Bernoullis Principle as well, which states that fast-moving fluids or air, such as strong winds, have lower pressure than slower-moving air. In a hurricane, the fast flow of the air above the roof's shape generates the low-pressure area outside of the house. So this creates the pressure difference between the air outside and inside of the house, and eventually the pressure difference becomes so large that it is strong enough to pull off the roof of the house. And so the roof experiences the lift, and similar to the airplane wings, or when the airplane flies off the wind blows on the bottom of the wing is slower than on the top, and that creates lower pressure on the top and high pressure on the bottom, and that lifts the airplane. So this was Bernoulli's discoveries, and he lived in 1700s, and there are many different discoveries that he did. But let's look at the equation that Bernoulli discovered, and it's all about the conservation of energy. Look at the equation. Before we actually look at the equation itself, I want to derive as much as possible, and so it is based on conservation of energy. So what I'm going to do is to write the conservation of energy. So here is the pipe, and in this pipe I'm going to look from the case of the molecules. So from this pipe I have V1 and A1 and pressure 1, and then at the second point on the top, so here's the point 1 and here's the point 2, and at the second point on the top I have V2, area 2, and pressure 2. So for conservation of energy, I have the change of the kinetic energy, and that will be equal to 1/2. And so talking about the mass of the, let's say, each molecule of the water, or the volume of a certain amount of water. So I have the mass and V1 squared. So that, let's say, changes of V2 mass, and minus 1/2 the mass V1 squared. So when the object goes, or some amount of water, the volume of water goes from one place to another, it changes its potential kinetic energy, and because the velocity changes. So then I'm going to replace the mass with density times the volume. So I have 1/2. Instead of the mass, I have density times the volume of the water that I'm looking at, that is moving. So let's say this is the volume. So that's the volume of the water. And then V2 squared minus 1/2 the density V and V1 squared for the velocity. And then there's also change of the potential energy. The potential energy is equal to mgh. So I'm going to call this H2 and this H1. H2 minus mg H1. And because we also talking about the volume of the water with the density, so mass is going to be replaced with density volume GH2 minus density volume GH1. And the work is equal to force that is pushing the water at the bottom, the distance x. So I'm going to say force 1, the distance 1, x1, minus force 2, distance 2. So the change of the in how much force is moving a certain amount of water is the work done on the, or energy change done on the water. So that will be equal to, force is equal to pressure times area. So I have P1 area 1 delta x1 in minus P2 A2 and delta x2, and area times the delta x is also the volume. So this is part of the volume, so I can say that the work is equal to P1V minus P2V. But the work is also equal to change of the kinetic energy plus change of the potential energy. So from here, this is where our equation will come. So the work, I have P1V minus P2V equals to change of the kinetic energy. I have 1/2 rho V, the velocity, squared 2, minus 1/2 rho V, the velocity, squared 1. The potential energy is rho V GH2 minus rho V GH1. Every single one of these terms has V, so I can cancel all the V's. And after I rearrange them in this equation, I will get Bernoullis equation. And what helps me to remember is that it does look like energy, the one that we learned before. So you have P1 on one side and you have P2 on the other side. So that's the pressure outside, the pressure in area 1 and the pressure in area 2. Then I have kinetic energy, which is 1/2 rho V squared on both sides. So I have rho V1 and rho V2. And I have rho GH and rho GH on both sides. So, and it's all based on conservation of energy. So let's look at the another application which is very interesting. Let me show you another picture where you can see how it also works. So here's another interesting application. In this area you have higher pressure, so the water is going to rise higher, and in this area you have lower pressure, so the water is going to rise lower. And in this area, again, looks like it is more pressure than the first one, but less pressure than in the second one. So it still rises high, but not as low or as high as before. So here's another interesting application that is used with Bernoullis Principle. Let's look at one of the first questions using Bernoullis Principle. A bullet misses its target and penetrates the town water tank, causing it a leak. If the water of the tank is open to the atmosphere, that means atmospheric pressure 10 to the 5th Pascal, determine the speed at which the water leaves the hole when the water level is 5.5 meters above the hole. And the second one, what does this stream hit where does the stream hit the ground if the hole is 3 meters above the ground? So the pressure initial and the pressure outside is P sub 0. So for Bernoullis equation, I have, maybe I'm going to write the Bernoullis equation first. So I have P1 plus 1/2 rho V1 squared plus rho GH1 is equal to P2 plus 1/2 rho V2 squared plus rho GH2. So in our equation, we have P sub 0 initially plus 1/2 rho V right here on the top. We're gonna call it, this is our y2 and this is our y1, so on the top is gonna be 2. So it's rho V2 squared plus rho GH2. So that's our initial start point of the water. And then where the hole is, we have again P sub 0 plus 1/2 rho V1 squared, and this is the velocity of V1. And then plus rho G, and this one is H1, the height where the hole is. So P sub 0 and P sub 0 can be cancelled. Also, V2 and V1, very often the speed at which V2 is moving down is much slower than compared to V1. So often on a short amount of time, V2 velocity on the top of the water tank is going to be not visible to go down when V1 is very fast. So often they drop this term because it doesn't affect it as much in a short amount of time. And we're looking at a certain instant when the velocity is V1. So what I'm going to be left is with this. Rho GH2 is equal to 1/2 rho V1 squared plus rho GH1. Every single term has a rho in it, so I can cancel rows as well. And what I'm left is with V1 is equal to the square root of 2g, and then I have y, or h, we started calling it h, so let's call it h2 minus h1. That is the same as the square root of 2ad, which is the square root of 2gh. If I plug in my numbers, I will get the velocity at which the water leaves the hole, 3.16 meters per second. And the time to fall, let's do maybe in different color. So it will land at the velocity v final. So to calculate v final, I have the square root of 2g, and that is y1, and that will give me the velocity of 7.746 meters per second, and this is when the hole is 3 meters above the ground. So the time it takes to fall on the ground is the change of the velocity over the acceleration, gives me 0.775 seconds. And from here I can calculate the distance, how far away from the tank will the water land. So this distance, let's call it dx. So dx is equal to v1, at which the velocity leaving the tank, times the time. So I will get velocity at which it leaves the tank and the time. So I have 316 times 0.775, and that is equals to 2.46 meters. In this question, they ask at what depth below the surface of oil relative density 0.8, which produces the pressure of 120 kilonewtons per meter squared, or 120,000 Pascal, what depth of water is it equivalent to? So at first, let's determine the density of oil. So the density of oil is 0.8, the density of water. So this is oil. And that is going to be equal to 0.8 times 1,000. And that is 800 kilogram per meter cubic. So I have the density of the oil. And the pressure formula says that it is equal to rho GH. And they say that the pressure produced by the oil, we don't include the atmospheric pressure, so they only say the pressure produced by the oil is equal to, and here the pressure by the oil and the density of the oil and the height of the oil, and that is equal to 120 kilopascal, 10 to the third Pascal. So if the density of the water is known and G is known, I can find the height of the oil that will produce this pressure. So I have 12 10 to the fourth divided by the density of the oil, which is 800, and times G, which is 10. And that gives me 15 meters. Also on AP exam, you can use G as 10 or 9.8, it's up to you. And now I want to figure out what depth of water will produce the same pressure. So for the pressure of the water, if it was the same pressure, it's density of the water, GH of the water. So the density of the water, the pressure of the water would be the same, so which is 12 10 to the fourth. The density of the water is 1000 times 10, and H of the water. So from here I can see that the height of the water is going to be only 12 meters to produce the same pressure at the bottom of that amount of water. In this question, they say that a manometer connected to a pipe indicates a negative gauge pressure. That means the pressure inside of the gas is lower than the pressure outside. That means that the gauge pressure is by 50 millimeters lower in height for the inside of the container than outside. And they give you the mercury density. What is the absolute pressure in the pipe in pascals if the atmospheric pressure is given 1 atmospheric, which is 10 to the 5th Pascal? So the atmospheric pressure is 10 to the 5th. I fixed this part. It's 10 to the 5th Pascal. And so that's what we know. And absolute pressure is the gauge pressure plus the atmospheric pressure. So the absolute pressure is the gauge pressure plus the atmospheric pressure. And that is equal to rho GH. So this caused by the difference in the pressure between atmospheric and absolute inside of the gas tank. So that is the gauge pressure. And plus the atmospheric pressure. So I can write atmospheric pressure. So that gives me, and I know it's negative gauge pressure, so it's negative. Rho is 13,600. G is 10, and H is 50 millimeters, so it's 0.05, and plus the atmospheric pressure, which is 10 to the 5th. And I get the absolute pressure is equal to 93,200 Pascal, or 0.932 atmospheric pressure. So if the pressure in the atmosphere is 10 to the 5th Pascal, then the pressure inside of the container is lower, and it's 0.932 of the atmospheric pressure, and the pressure gauge is going to move down by 50 millimeters to indicate that the pressure inside of the gas is lower. In this question, they say that the spring is attached to a cube of wood, and they give you the density of wood, of volume. They give you the density of the volume of the cube that is placed in the fresh water, and the density of the water is also given, as shown in the figure. Calculate the tension in the string. So what we're gonna do is to write the forces that are given. Actually, they already did it for you. The forces that are given by everything that is acting on the cube. So I have the tension, which is acts down, and I have a force of gravity, and I have the buoyancy force, and the cube is in equilibrium. So I have the buoyancy force minus the tension force, and minus mg is equal to 0. That means the tension force is equal to the buoyancy force minus mg. And they ask me to find the tension force. So now I have the tension force is equal to the buoyancy force is the force displaced by the water that when the cube is in the water. So that's the mass of times the g of the water, the weight of the water. So I have the mass of the water, g, minus mg of the cube. The mass of the water is the density of the water, and the volume of the cube, g, minus mg of the cube. They don't give me the mass of the cube, so I can also replace the mass of the cube with the density part. So it's the density of the cube, the volume of the cube, and g. So the tension is equal to the density of the water is 10 to the 3rd. The volume of the cube is 0.125. And then I have 10 minus the density of the cube. It's made of wood, so it's 750. The volume of the cube is 0.125, and g is 10. So from here I see that the tension acting on the string is going to be equal to 312.5 newtons. In this question, they say the water intake at a hydroelectric power station has a 1 meter diameter, and the inflow rate is 0.4 meters per second. So the inflow is the velocity at which it comes into. So we have 1 meter diameter, and the velocity is given. The inlet to the turbine at the generator building has a smaller diameter, and the flow rate is 9.5 meters per second. So the one at which it's coming out is 9.5 meters per second. And the question is, what is the pressure difference between the inlet to the turbine and the intake? So let's call this height h, the one that is given. So we have the diameter of the incoming water, we have the velocity of the incoming water, we have the height, and we have the velocity of outcoming water. So I see it's a Bernoulli type of a question. So I have P1 plus rho GH plus 1/2 rho V1 or in squared and equals to P2 plus rho G, the height at where the water is coming out is 0, and plus 1/2 rho V out squared. So this one cancels, and we need the pressure difference. So we need P1 and P2 difference. So P1 minus P2, that's what they asked, the pressure difference, is equal to rho GH. Well, let's do it this way. It's 1/2 rho V out squared minus V in squared, and minus rho GH. So P1 minus P2 is going to be equal to 1/2 times the water 1000. V out is 9.5 and in is 0.4, and minus 1000, or times 10 gives me 10,000, and the H is 180 meters. So from here I find that the change of the pressure is equal to negative 1755 kilopascal. In this question they say that water flows through a pipe as shown. At the lower elevation, the water speed is 5 meters per second and the gauge pressure is 7.5 10 to the 4th Pascal. Find the speed of the water at point B. So they mean this one is the point, the top one is point B and the bottom is point A. And find the gauge pressure at the higher elevation, which is point B. And the diameter of the A point is 6 centimeters, and the diameter of the B point is 4 centimeters. And the relative to A point, the height is 2 meters. So I'm going to use Bernoulli's equation as well, but I do not know the velocity V2. So to find the velocity at point B, I'm going to use the continuity principle, and I have A1 V1 is equal to A2 V2. So the area is pi r squared, and they give you the diameter, so you can figure out the area 1 or A and B. And then you can calculate the velocity at V using the continuity formula. And then you can plug it into Bernoulli's equation. So here I plug in this velocity. And then after my calculations, I'm going to get that the pressure at P2 when I plug in my numbers. So the pressure at 2 or B, this pressure is B, is equal to, so here if I simplify my equation, or you can right away solve this one for PV, I decided to simplify it a little bit and plug in the numbers again. So I got 4,219 kilopascals. So 4,219 kilopascals. And that is the pressure at the point B at the top of the pipe. And that will conclude our lesson on fluid mechanics for our video 4. Where we introduced Bernoulli's equation and tried to solve it to solve problems involving Bernoulli's equations. Thank you for watching this video, and I will see you in the next one.